Let's go in the Wayback Machine. Way back in Lecture 15, we were talking about sets. And we were looking at the IMDb database. And what we wanted to see in Lecture 15, and we're going to kind of work through this, extend this going forward today. But what we wanted to see was if we go back into the IMDb file and we want to find out how many unique names are in the file, how could we use a list and then a set to actually resolve that problem? And this is the code for the list. And what we said was we would create a list. And as we walked through the list for every line in our file, we'd split it up. We'd pull off the name field. And if the name wasn't already in our list, we'd add it in. Right? And this was the list solution. And we ran this on the Hanks. And by the way, this is essentially the code from the website. So if you go down into here, into code written in class, this is essentially Lecture 15 code using lists to hold unique names. So, this is essentially that code there. But what it actually does is we just walk through. If the name's not already there, we add it, and I put in some debug stuff. Here's a start time and an end time, so we can measure how long it took us. Right, end minus start is the amount of time that's elapsed, and then at the end we just print out how many different people we found, and we can run this. And I'm running it right now on the Hanks data test hanks.txt. And if we do, what we find out is that in the Hanks data test, it took us about 7,000th of a second to find 13 different people. And if we run it again on IMDb 2010 through 12.txt, what we get is, well, now it's slowing down a little bit. We are going through, and every 1,000, right? Every 1,000 we're kind of printing out just so we can measure some kind of progress. But things are slowing down. And the thing that I want you to notice here is that as we walk through, as we add more and more names here, as we get up to 20,000 names in our name list, right? This is how many names we've seen in the file, and this is how many unique names we have. As we get up towards 20,000, things start getting a little slower, and for that data set, we're now sitting at about 18 seconds. And it's starting to get impractical, but we did find 20,455 different people. And we could do this again, and we can actually do this with the full data set, IMDb data. This is about 260,000 names. 120,000 or so are unique, but we can do IMDb data.txt. And what we're going to find out is that it starts slowing down more and more. The first 10,000 iterations go by pretty fast. The second 10,000 start taking a little longer. And what we're going to see is that this kind of pattern repeats, and it gets slower and slower and slower and slower at each iteration. And the reason it gets slower, as we discussed, is this line right here. If not name and name list. In order to find out if a name actually sits in the name list, what we have to do for a list is we have to go through and we have to walk through the list one element at a time, and we have to see, is the name actually in the list? Is the current place we are in the list equal to the name we're looking for? And if not, we would get all the way to the end. Right? So this single line walks through the entirety of the list. After we've walked through the entirety of the list, if we don't find it, then we append on, and now our list has just gotten longer, and we'll actually have to do more work the next time through. And you can see that this is getting, well, it gets pretty slow, and I think this comes down to be about 370 seconds or so, 6 minutes. All right, so we use this to introduce this concept of sets. And here's the set code. I'm going to keep this running for a second while I talk about the sets, but I'm probably going to kill it before it ends. You can see that now each iteration, every new 1,000 words we read takes a substantial amount of time. All right, so what do we want to do with sets? Well, we said that sets have the property that they maintain uniqueness. And we said that they maintain uniqueness very quickly, or it doesn't take much time. And we did something, we could do something like if name in name set. I think this is the code we originally had. We could put this in, but what we talked about was the fact that since name manages uniqueness, we don't actually need this line at all. When we try to add something that's not unique, the set's going to refuse to add any additional copies of it. It's just going to say it's already there and kind of go on from there. But we'll leave this in for now. I'm going to kill this. You can see that it's taking a lot of time. We can get back to running that later if we want to. But this looks an awful lot like this, right? At this point. Instead of name list, we have name set. And if not name and name list, this should say not name and name set. Good catch. If not name and name set. So, and instead of the append, we do the add. Right? So essentially this is the same, really the same code. And we'll keep for right now at least, we'll keep our printout in here. Do a Control S. And now I'll run this set version, and we'll run it on Hanks. Right, and Hanks.txt, it took, 7/1000ths of a second the first time? Somewhere in there. 7/1000ths of a second. Well, it takes, on the set one, it takes 5/1000ths of a second. 2/1000ths of a second, we're probably not going to notice, at least not immediately. We can run it again on the IMDb data, the IMDb 2010 through 12 data. Right, and if we do that, well, now we found our 20,455 unique people in a quarter of a second. When we used the list, we found our 20,455 different people in 17 seconds. So now we've gone from a quarter of a second for the set case to, almost 18 seconds in terms of using the list solution. Right? So we're now, that's starting to become a significant savings. And we never did get to see the end of the IMDb data, but let's run it with the set version. And boom, we're done. 2.4 seconds, 2.42. So that's significantly faster. Let's come in here just and put that down a little bit further. What happens if we kind of comment out this printing code? Because, really, the printing code was just because the list solution was so long that we wanted to see how long it took. And while this doesn't take up much overhead in terms of printing a list, it actually does start taking up overhead in terms of the set solution because the set is so much faster. So let's see what this gives us. IMDb data.txt. And we can get this down to less than a second, 0.98 seconds, to find 120,705 different people. So sets are faster than lists. The issue is that sets maintain uniqueness, but they don't maintain order. So if order is important, and if you have to maintain order, for example, if you want the order that you read something in from a file, then you need to maintain it in a list. But if order doesn't matter, if just the existence or the non-existence matters, sets are essentially a lot faster. And we talked about that a little bit. Let me just quickly, before we waste too much time in this class, let me just give a little example. See if my handy-dandy camera is working. My son was using this this weekend. I think I got it fixed. There we go. So here's our whiteboard solution. Okay, so when we have a list, and we have a list of items, right? So we start out with something like this. We have a list of items. Oops. Why is my board dropping down? Okay, there we go. We have a list of items. We're storing them in a linear list. As long as we're appending, we're putting things on the end. If we know how big the list is, putting something on the end is pretty fast. But in order to determine uniqueness, we have to check here, check here, check here, check here. So we have to go through every item of the list and figure out whether the item, whether the entry we're looking for is there or not. For sets, it's kind of different. You can consider sets as a whole big, long list. And when you get a value like Hanks, Tom, what we do is we apply an algorithm to this called a hashing algorithm. And it turns this into an index. And the algorithm we use will take any string of letters like Hanks Tom and turn it into, we'll turn Hanks Tom into the same index every time. So now, instead of having to search through this entire list, we go to index I, we look, we say, is Hanks Tom stored here? If not, we're done, right? Then we just have to add it in. If it is there, well, then we're also done. Then we know that it's already there. We don't have to do anything else. So it turns this from being an order of n operation, where n is the length of the list, to an order of 1 operation, or a constant time operation. We only have to check, in general, in the average case, we only have to check 1 index. And because of that, access to entries in sets, testing membership, etc., in sets can be very fast. And calculating things like unions and intersections and other set operations are largely done using this type of membership test. So, that's why sets are really fast. Now, the drawbacks. Uniqueness, right? There's no method in here for determining how many Tom Hanks you have in there. So one Tom Hanks is the same as any other Tom Hanks in a set. The second, it can only store, unlike lists, which can store any type of data element, you have to be able to calculate this hash function. This function that converts from Hanks Tom into an index is called a hash function, and you have to be able to calculate this hash function on your data elements. So it's not possible to store any arbitrary data type in it. It has to be something hashable. Now, Booleans are hashable, tuples are hashable, floats are hashable, ints are hashable, lists, tuples that don't include lists are hashable. Yeah, I think. I never tried it with a tuple that does include a list. But tuples of values like integers, etc., are hashable. Strings are hashable because they're immutable. Okay, so there's a tuple with a list in it. Yeah, okay. So tuples that consist of hashable types are hashable. tuples that include unhashable types, such as lists, are not hashable. Okay, so be careful with that. But in general, what we have to do is we have to limit the values that we can store in sets. But if we do that, then we get this really fast access. And it allows us to do algorithms like this list algorithm, or like this, finding the unique names in the IMDb data file. It allows us to do this really quickly because this becomes a constant time operation. And in fact, like I kind of alluded to, we don't even have to do that because sets require you, it does the check before it puts it in. They require you to be unique, and this will work just as well. Okay, 1.4 seconds this time. All right. So that is kind of what we're talking about. Let's go over this just one more thing. This is a constant time operation. So if there are n lines in our file, if our original file, right, it has like 260,000 lines in it. So we have to go through this outer loop 260,000 times. But every line in here is essentially a constant time operation. None of these depend upon the size of the list, including adding a new element, a new unique element to the list. So this is accessed n times. Everything in here is accessed one time. N times 1 is n. That gives us something that is considered order of n. And you'll see notation like order of n. Okay? When we go to our loop solution, this line, name, in fact, this specific clause of this line, name in name list, depends upon the size of name list. So for our analysis, this name list is about the same size, right? It's 120,000 versus 260,000. But if we assume it's 75% of the size, if 75% of the names in that file are unique, then it's about the same size as order of n. So this takes n time, right? We have to go through this outer loop n times. And as we get big, we have to go through this inner loop n times. Okay, so this inner loop gets executed n times for here, and then n times, right? It takes n times to go through a single iteration, and that happens n times. So that becomes an order of n squared algorithm. And we'll talk about this a little bit more as we go through, but those are the two. This is a loop of a loop is generally order of n squared. It could, just leave it at that. If, however, there's no loops in here, if this is just a constant time operation, then it's order of n. And we'll kind of talk about this as we go through and develop some intuition. And before you start saying, but it starts out being, this list starts out being very small, right? In the beginning, it's time 1. And at the end, it's, on the order of n, right? So the average would be n minus 1. That's the average entry times n entries, and then divided by the number of entries. So it's n squared minus n. The average time to go through that loop to execute this line is order of n minus 1 on average, or n minus 1 over, n minus 1 over 2, not over n. Right, so at the maximum it takes time n, at the minimum it takes time 1. N minus 1 over 2 is the average amount of time it takes per iteration, and if you do this n times for the outer loop, then it is n times n minus 1 over 2. We drop all the constants, and that's order of n squared. And we'll talk about this again. Don't get too hung up on this right yet. We will have a number of opportunities to talk about this before we're going to test you on it. But I just want to throw this out there and kind of give you as an initial analysis of where the time goes. All right. And yeah, that's pretty much what we want to talk about. All right. Let's see what we have here. Anything here? Nothing. Okay. So